Hello everyone, and welcome to this training video. Through this video, I will guide you through the methodologies and tools used to monitor and evaluate the impact of nature-based solutions within renewable energy communities. This session is part of the EnerCmed project, which focuses on sustainable energy transition and climate resilience in Mediterranean port cities. Before going into the technical content, I want to briefly introduce the context of the EnerCmed project. Our main goal is to combine the reduction of energy poverty in vulnerable areas with nature-based solutions that can mitigate urban heat islands. The project is implemented in 5 residential port city areas across Spain, Croatia, Greece, and Italy, through training, capacity building, and technical assistance. The key actors are Mediterranean municipalities, urban authorities, and local stakeholders engaged in energy transition and climate adaptation. This training module provides an integrated overview of how nature-based solutions can enhance climate resilience and improve the performance of renewable energy communities. Across a series of videos of the module, we introduce the main NBS types, explain how they can be designed and integrated at community scale, and discuss the methods used to assess their performance in terms of microclimate improvement and energy efficiency. Urban areas can easily become heat traps, especially during summer. Cities tend to be significantly warmer than the surrounding rural areas because of the materials and dense building structures that absorb and retain heat. This results in higher heat stress for people, especially vulnerable groups, and it increases the energy required for cooling. Nature-based solutions, such as trees and vegetation, offer clear benefits. They provide shade, enhance evapotranspiration, improve air quality, and ultimately help lower temperatures and improve outdoor comfort. But the key questions are, how do we know which type of NBS is the most effective for each study area? And how can we quantitatively assess the cooling impact of vegetation? This is exactly what the next part of the presentation will explore. When we evaluate nature-based solutions, it's important to understand that cities operate at different spatial scales, and each scale reveals different microclimate processes. At the street scale, roughly 100 meters, we look at very local conditions. This is where shading from trees, the width of the street, and the height of buildings have the strongest influence on temperature and wind. At this scale, we can observe very detailed interactions between NBS and people's thermal comfort. At the neighborhood scale, around 1 kilometer, we start examining how multiple streets, open spaces, and building blocks interact. Here, patterns such as ventilation corridors or areas of stagnated air become visible, and NBS interventions need to be coordinated across a wider area. At the city scale, up to 10 kilometers, we look at broader phenomena, such as the urban heat island. At this scale, we assess how the overall distribution of greenery, urban density, and land cover influences temperature patterns across entire districts or cities. To study these different scales, we rely on 3 main methodological approaches: field observations, measuring real-world conditions directly in the study areas. These measurements give us ground truth data for temperature, humidity, wind, and comfort levels. Experiments. Physical or controlled tests, such as wind tunnel models, allow us to isolate specific variables and better understand how vegetation or urban form affects airflow and shading. Simulations, numerical models like CFD or GIS-based tools help us evaluate different NBS scenarios and understand their impact across each scale, from individual streets up to the city level. By combining scales and methodologies, we can build a complete and scientifically robust evaluation of how nature-based solutions influence urban microclimates. In evaluating nature-based solutions, we rely on 3 main scientific tools, each contributing different types of information about the urban environment. First, particle image velocimetry. PIV is an experimental technique typically used at the street scale. It helps us understand fundamental fluid mechanics, in simple terms, how air moves around buildings, trees, and urban features. By studying airflow patterns, we can see how vegetation influences wind direction, turbulence, and ventilation at a very detailed level. Second, computational fluid dynamics. CFD is a numerical simulation tool that produces high-resolution results in complex 3D urban environments. CFD can be used at both street and neighborhood scale, allowing us to simulate different NBS scenarios, like adding trees or shading structures, and see how they affect temperature, wind speed, radiation, and thermal comfort. It is one of the most powerful tools for testing what-if scenarios. Third, Geographic Information Systems. GIS works at the neighborhood and city scale, where we analyze large patterns related to land cover, greenery distribution, surface materials, and the urban heat island effect. GIS is ideal for large-scale climate analysis, helping us understand how NBS influence temperature patterns across whole districts or cities. Each tool is suited to a different scale and type of analysis. Let us now focus on the first tool used to evaluate nature-based solutions, particle image velocimetry, or PIV. PIV is an experimental technique that is particularly useful for understanding fundamental fluid dynamics within urban environments, especially airflow around buildings and vegetation. The main goal of using PIV in this context is to quantify how vegetation influences air circulation at the street scale. To do this, we create a scaled-down physical model of an urban environment and place it inside a controlled water channel. The flow is seeded with small tracer particles that move with the fluid. A high-speed camera is then used to capture the motion of these particles over time. By tracking how the particles move between successive images, we are able to reconstruct the flow field. Through post-processing, this particle motion is converted into velocity fields. These results provide detailed and quantitative information about airflow patterns, such as wind speed, direction, turbulence, and areas of enhanced or reduced ventilation. This level of detail helps us understand how trees and other nature-based solutions modify airflow and contribute to improved urban microclimate conditions. This slide presents results from a particle image velocimetry experiment conducted at the University of Cyprus, examining the aerodynamic effect of trees on airflow within an idealized urban street canyon. 4 vegetation scenarios are analyzed, ranging from no trees to large trees, considering only the aerodynamic influence of vegetation, while shading and evapotranspiration effects are excluded and addressed later through numerical simulations. The approaching wind is perpendicular to the canyon. Airflow patterns are shown using velocity contours, with colors ranging from blue for low velocities to red for high velocities, and streamlines illustrating flow direction. Without vegetation, a strong vortex forms between buildings, promoting air circulation. The introduction of small trees alters the vortex position, reducing airflow at pedestrian level, while medium and large trees further slow the flow and divert air around the canopies. Overall, the results highlight that tree size significantly influences airflow structure and urban ventilation. While particle image velocimetry provides detailed insight into airflow behavior under controlled experimental conditions, its application is sometimes limited to simplified geometries and aerodynamic effects. To study real urban environments and to account for additional physical processes such as heat transfer, radiation, and evapotranspiration, numerical modeling approaches are required. For this purpose, computational fluid dynamics is used as the second evaluation method. This slide presents a high-resolution computational fluid dynamics study based on a real urban geometry. The case study focuses on Ledras Street in the historic center of Nicosia, Cyprus, a dense and pedestrianized urban area. A detailed digital model was developed and discretized into approximately 22 million computational cells, allowing airflow and heat transport to be simulated within each cell. The simulations represent a typical summer day in July 2010 and provide spatially resolved results for key meteorological parameters across the study area. Trees are modeled as porous volumes to represent both aerodynamic and thermal effects, including shading and evapotranspiration. Although this approach delivers highly detailed and realistic results, it is computationally demanding. This slide presents the main outputs of the CFD simulations, with a focus on human thermal perception and its implications for energy consumption. Thermal comfort is evaluated using the Universal Thermal Climate Index, which represents an equivalent temperature describing how outdoor conditions are perceived by humans. UTCI integrates multiple meteorological variables, including air temperature, radiation, humidity, and wind, along with human-related factors such as clothing and activity level. The index spans conditions from extreme cold stress to extreme heat stress, allowing the identification of urban heat hotspots. Using this approach, the cooling effect of trees can be quantitatively assessed, demonstrating their role in reducing heat stress and supporting evidence-based urban planning and climate adaptation decisions. This slide presents typical summer results of thermal comfort, derived from CFD simulations for Ledras Street in Nicosia. Thermal comfort is evaluated using the UTCI, ranging from moderate to extreme heat stress. Air temperature measured at a nearby meteorological station is included for reference, while UTCI results within the street are compared for scenarios with and without trees. Areas with trees exhibit significantly lower UTCI values, indicating reduced thermal stress, whereas streets without trees experience much higher perceived heat. Around midday, differences in thermal comfort can reach up to 10 degrees Celsius between shaded and unshaded conditions. Although this modeling approach is computationally demanding, it provides very high-resolution and spatially detailed results, enabling detailed assessment and visualization of thermal comfort, including animated outputs. The third method is based on geographic information systems, which are particularly suitable for city-scale analysis, where CFD becomes impractical due to computational constraints. Unlike CFD, this approach does not require detailed three-dimensional building geometries. Instead, it works with spatial and temporal data layers that contain environmental information such as land cover, vegetation, surface characteristics, and meteorological conditions. By combining these layers, a city-wide map of thermal comfort can be produced using the Universal Thermal Climate Index, highlighting areas where heat stress is likely to be high or low throughout the day. This method is fast, scalable, and well-suited for supporting urban planning, as it allows city authorities to identify priority zones for nature-based solutions and cooling strategies without the need for complex numerical simulations. This slide presents city-scale results of human thermal comfort derived using geographic information systems for the entire city of Nicosia during a typical summer day. The animated visualization shows the temporal evolution of the Universal Thermal Climate Index, allowing thermal comfort conditions to be assessed across the whole urban area. Distinct spatial patterns can be observed, with lower thermal stress in city parks and vegetated areas, and higher thermal stress in densely built urban zones. These results highlight how land use, urban density, and green infrastructure influence thermal comfort at the city scale, demonstrating the value of GIS-based approaches for identifying heat stress hotspots and prioritizing areas where nature-based solutions can be most effective. This slide summarizes how combining different methodologies across multiple spatial scales supports informed decision-making for nature-based solutions. At the street scale, experimental and high-resolution numerical approaches provide detailed understanding of airflow and local microclimate processes. At the neighborhood scale, CFD enables the evaluation of thermal comfort and heat mitigation performance in complex urban environments. At the city scale, GIS-based methods reveal large-scale thermal patterns and identify priority areas for intervention. Together, these multi-scale results form a robust urban micrometeorological framework that supports effective nature-based solution design, improves urban microclimate and air quality, enhances thermal comfort and public health, and provides strong scientific evidence for urban planning and policy development. Thank you for watching. To learn more about the EnerCmed project, access related materials, and explore further resources on nature-based solutions, please scan the QR code.